What's up, everybody? Welcome to Earth Science. We've got kind of a big one to tackle here. We've got to look at a whole bunch of different interactions between these tectonic plates. So let's open up, just like remembering where we've been so far here in tectonics. And it's stuff that should be done. All of these notes above where we're at right now, which is page 6, should all be done. Let's talk about what's going on. The very outside of the Earth has this rigid, crunchy layer, and below that is a softer layer. And we broke that down a little bit better right here. Crunchy, squishy is really like the nature of it. So picture a Skittle. This is like the Skittle model of the Earth. If you squeeze a Skittle, the outside of it will crack, whereas the stuff down below will kind of mush and deform. You're not going to say it's a liquid. Skittles aren't liquid on the inside. They're solid, but they can squish, right? Now that ignores the core and everything way down there, but for purposes of like near the surface, that's a pretty good analogy. So that cracking is going to be what leads to what we detect as an earthquake. When that crunchy outer shell cracks, because it's moving around and it's under pressure, it's moving over a curved surface and maybe banging into another piece of crunchy earth surface, or maybe sliding past it. And every time that there's that motion, it pushes, can't move, and then slides. That produces enough energy for an earthquake. So the Earth has this rigid outer layer. What was that called? Lithosphere. And a softer layer below that's astenosphere, A-S-T-H-E-N-O sphere. And this rigid layer, the outer layer, is broken into pieces. And remember, crustal plates is the term I don't really like because it's not crust, it's lithosphere. So we call them lithospheric plates, is the long and fancy one, or what you may have heard in your days. Tectonic. It's just as good and probably easier. So with all of these tectonic plates all moving around, we've got a whole bunch of different interactions. We should hopefully, because you did the first lab of this marking period, have the idea that we've got 3 different groups of them. We've got Convergence, where plates come together. That's like going on up here through these Aleutian Islands coming off of Alaska. We've got Divergence, where plates are spreading apart. That's happening through the center of most of the oceans. Maybe not exact center, but through the middle of many of the oceans, they're spreading. And we've got Transform, where plates are sliding past each other. The one that most of us are familiar with is the San Andreas faults running through like central to southern California. 2 plates sliding past each other. But now we're going to complicate life, because not only do we have those 3, but what we've got to remember is that from this section right here, we've got 2 different kinds of crust. So again, you should have already done this. You should have dealt with this in previous work. Don't jump ahead. If you have jumped ahead, it's gonna start going fast. I'd pump the brakes now, go back and finish the other stuff, and then come back to this. We've got 2 different types of crusts: continental crust and oceanic crust. Now, this reference table covers the idea that the oceanic is more dense at 3.0. The continental is less dense at 2.7. That's going to be important. Another thing this reference table doesn't cover, unfortunately, and it was on the quiz, and I give you a hint on the quiz because that wouldn't have been fair, is that the continental crust is thicker. So maybe scroll back up and check this in there, because why not? It's very important for what happens when these things interact. When 2 things hit each other, these 2 differences make a large difference in what happens. Continental is thicker but less dense. Oceanic is thinner but more dense. And at the end of the day, if you can wrap your head around this, that leads to this idea of a balance in the astenosphere. Isostatic balance is the fancy term for it. The thing that doesn't weigh as much, there's more of. The thing that weighs more, and I'm simplifying density, but the thing that weighs more, there's less of. Therefore, there's like this balance. It's like that silly question. You ever hear anybody say, what weighs more, a ton of feathers or a ton of lead? You would need way more feathers to make a ton, but it's still a ton, right? So there's this balance between those 2. But when they interact with each other, it's going to start to get messy. So we've got to go through and figure out, okay, what happens with divergence when they're on continental crust and oceanic crust? And then more complicated, what happens to convergent plate boundaries when plates come together when you've got all three of these conditions: oceanic running into continental, oceanic running into oceanic, or continental running into continental. Finally transform, although that one honestly is pretty easy. There's not a whole lot of interactions there because the two types of crust. It's just sliding past. That one we can kind of say, it's good. And how do the Hawaiian Islands form? I don't suppose I'll mention that a ton today because we've got enough other work ahead of us. And you've already done the Hawaiian Island Formation Lab. So that's great. So today's goal is what goes on where these plates interact, especially like in understanding them in cross section. Or maybe it's easier to understand in profile. Okay. This map is map view. We're going to look at this area specifically. We're going to look at where this Nazca oceanic plate runs into the South American continental plate. But we're looking right now down onto a map in map view. What would happen if I could pick up the map and really the Earth and look at it from the side? Say, what happens in side view as these two plates run into each other? And really, this is going to be like, if it's day one of Earth science, and we're saying we're trying to figure out why does the Earth really look like this? This lesson that's going to be over the next couple of videos is probably the biggest thing in terms of why does the Earth look this way? Why are there these mountain ranges and these mountain ranges and these mountain ranges? Why are the oceans shaped like this? Why does South America and Africa kind of look like they maybe lived together at one point? They did. This is like giving us our big overall large scale landforms here on Earth. All of this talk about tectonics. So let's look at Google Earth real quick. You can also see that this is where a lot of earthquakes are taking place. All these little dots, this is a live feed of the last week, all earthquakes from 1.0 up. Now, 1.0 is very small. You wouldn't really notice that. But from 1.0 up over the last week, you can see that there's a whole bunch running through that San Andreas area. Decent little cluster right there. Some underneath the Cascade Mountains right here. There's mid-ocean ridge, transform fault, mid-ocean ridge, subduction. These are all things you're going to have to figure out in the next, through the next lesson, next day or two. Up here to Alaska, same thing. There's a subduction zone here. Crazy amount of earthquakes happening because of the subduction along this dark line right there, this trench. And we'll think about that. All right. And again, this is where there's like a value in looking at the Earth tectonically. Don't look at it with geographic borders that we've invented as humans, as societies. Look at it through it like a tectonic lens. We live on a plate that starts way over here at this mid-ocean ridge, and then there's some noise through here, and then way over here to this edge, and we live almost dead center. We live up here where I have some of these marks. So we really live like we're that far from a plate boundary, and we're that far from a plate boundary, which is why we're pretty safe tectonically. Not a whole lot of earthquakes happening. Get occasional small ones in mountains and things like that, but nothing too large. Okay. So this is going to take a little bit. I'm gonna do these each as a separate video so that it's easy to pick up and drop off wherever you left off. But we're going to try to nail this page 7 right here. All of this, I'm going to try to get this all onto one lesson. And let me sneak preview what the assessment's going to be. This is what we're looking at, are these cross sections. What do these things look like from the side? So your job is going to be at the end of all this, please don't go ahead to the quiz. I don't want to see the quizzes get done until I see your drawings on your notes. Otherwise, I'm just not going to count the quiz. It's not, so you're not gaining anything. So you'll have to say, okay, we did this drawing. What is that? Is that divergent or convergent? And is it continental, oceanic, or is it one of these combinations? You have to do that. So there's 5 of them. And then you're also going to have to, that's 1 through 5, for 6 through 10, take the same 5 drawings and say, where on earth is this something that's happening? That's is a challenge. This is not easy, but if you do the notes, it's all going to be sitting right here on one page of your notes for you. Okay? That's my expectation. Do not go ahead of the quiz. It will not go well. All right. So that'll be good for now. There's our intro. I'll stop this, follow your survival guide, work all of these things, and you will be in good shape. All right. Good luck with it. Take your time. It's a lot. Stand up, stretch, take a breather, take a break here and there. and you'll do well. All right. Good luck, folks.